How are we now? Are we good? Okay, great. Thanks, Jonathan. Again, all I did was I imported my sync kernel function from my SciPy2013 file, and what I want to do conceptually is make this into a universal function in NumPy. Okay, I can't give sync kernel a NumPy array directly because you get this error. Value error: the truth value of an array with more than one element is ambiguous. Use a.any or a.all. And what's going on here is we're comparing a NumPy array to a value which gives us back a Boolean array. And then when you use that inside of an if test, NumPy raises this exception. Okay. Oh, yeah. That's good. Let's try that. Okay. So again, the A up here was just a linspace, so just a NumPy array. And I called sync kernel with A as an argument. Okay. So what we need to do to fix this is create a version of sync kernel that's called for every single element of a NumPy array. And fortunately, NumPy comes with a decorator called Vectorize. Vectorize is this fantastic tool. Unfortunately, its performance isn't as great as you'd hope, but the idea of Vectorize is great because it allows you to take a little kernel, like we have here, sync kernel, that takes scalar arguments, and it will run that kernel for every single element of our NumPy array and build up a new NumPy array out of the results. Okay? So let's try that. We can say sync equals vectorize sync kernel. So again, I pulled in everything from NumPy. So I did from NumPy import star. So that's why I can just use the vectorize without a prefix. So now I have this function sync. And now let's try sync of A. And that works. Okay. So it's doing the right thing now because Vectorize takes care of taking a NumPy array as an argument, calling our sync kernel for every element of that array, and creating a new array out of the results. Okay. So let's time it. Well, I don't want to get ahead of myself. I just want to show you what's going on here to motivate our exercise here a little bit. Let's look at test sync.py. Oh, sorry. Again, I'm getting ahead of myself. Let's look at the README file first. Okay. So we're just going to be adding simple type information to a def function, our sync kernel, to speed it up using Cython. Okay? And so the file SciPy2013 defines a simple function, sync kernel. It's designed to be vectorized with NumPy's vectorize decorator. NumPy, so it's just describing what I did before. So since our sync kernel function is pure Python, it's going to be slow. There's a lot of Python overhead for every single call. And we're going to create a Cython version of the same kernel function to speed it up. Okay? So now we're going to run test sync.py, which uses pix import to compile and import the Cython source files for this exercise. So you're going to use it like this, Python test sync.py. Okay? Let me just show you here briefly. This module is pulling in the right compiler, the right options for using this on Windows. So for those of you who didn't have success with pix import on Windows before, this should hopefully get around that. All right, so let's take a quick peek here. We're importing NumPy, time it to do our timings. We're importing pix import, and then we test and see if we're on Windows, and if so, we set up our right arguments. And this is essentially just sticking on the -- compiler equals MinGW32 onto our line there. And then we do pix import.install. Okay, and on Mac, on Linux, this is going to be, the argument's going to be nothing, and on Windows, it's just going to pull in the right thing. Okay. So now we pull in our 3 different versions of SciPy2013. Our pure Python version, SciPy2013, our sync kernel, which is our Cython version of the same thing, and then the solution version is the 3rd version here. So we're just going to time all 3 of them. So we vectorize the kernels inside of each one of these and get a Python vectorized kernel, a Cython, and a Cython solution one. Okay, so we've taken our kernels, we've vectorized them using NumPy.vectorize, and now we're creating a little NumPy array X, and now we're just timing the 3 different versions here. Okay, so that's all our test is doing. So let's try it out. Test sync.py. It'll run a little bit, and the pure Python time is about 40 milliseconds. The Cython time is measuring the time taken for the, which one is it? The sync kernel.pyx file. Okay, we'll take a look at that in a little bit. And the solution time, this is the end result of all our transformations that you're going to be aiming towards, is about 15 milliseconds or so. So let's look at the sync kernel.pyx. And all we're doing inside of here, we just literally took the same code that was in our Python file and we stuck it in here. So it's just, again, same exact code, we just essentially renamed the file to sync kernel.pyx. So now it's a Cython source file. Okay.
Did you just symbolic a link to a Python file? Change the name of symbolic link to pyx?
Yeah, you could. You could. I wanted to keep them separate so you can compare the differences, but yeah, you absolutely can. Let's see, where's my test? There it is. So again, just running it. You see, just compiling using Cython, in this case, gives us a little bit of a speed boost. Okay, so for free, we're getting some percentage speed up for this case. Not much, but some percentage speed up. Okay, again, it's this version here, this middle line, that's running our sync kernel.pyx file. Okay, so let's look at our README again for the next step. So step 2. The sync kernel.pyx contains an unoptimized version of the sync kernel function. So we're going to add type information so the sync kernel function takes a double and returns a double as a result. Rerun the test script and see if there's any difference in the Cython time. Okay, so let's give that a try. So let's look at sync kernel.pyx. Now, I'm not asking much here at all. Right? It's a simple lookup of previous slide to see how to convert this appropriately. So give you a little bit to work on that, and run the test again to see if there's much of a speed up. Okay. Okay, so it's pretty simple, right? It's just adding a couple declarations. So we can make this return a double if you want, and give it a double as an argument. Perhaps I didn't mention this before. You can type the return type of a def function if you like. It has to be compatible with a Python type for this to work. I wouldn't expect this to make much of a difference, but it's good for the sake of the exercise. You could make this a CPDef also if you like. Again, it's not going to make much difference in performance, but if there are other functions inside of this pix file that we're calling sync kernel, those other functions would call the fastc version of this function, not the Python version. So that would make a performance difference. Okay. So you're saying if I do double here, oops, it does not work. You're probably right. So I apologize for the confusion. Yeah. So yeah, def functions, I apologize. You're right. The def functions have to return objects for general Python objects. So you cannot you cannot type the return type for def functions, but you can for CPDef. Oh, okay. So it's even slower. So let's try the test sync again. So the version I did, I just added a single double here. And I got a little bit of a speed boost. Nothing significant though. Now we're sub 30 milliseconds on mine, whereas before we were like 32, 35 milliseconds. So it might not even be that significant. But so in this case, there's not much benefit since this is a fairly simple function. But does anyone want to take a guess? If you look ahead in the README, you'll have a good idea of what the next step is. But where a lot of the overhead is in this, the sine function, that's right. So we're using sine from Python's math module, and we're calling that sine inside of our function. So there's a lot of Python overhead there. Right? We want to get rid of that Python overhead. So how do we do that? What do we use to pull in C import, right? So now we're going to change. The next step is to say we want to pull in the sine function from the C standard libraries math.h. So we're going to say little what?
For the def, if you do CP def,
Mm-hmm.
it does make a difference.
For you, it may slow down other people. It may speed up others. It's going to be just we're in the very small wrapper layer overhead here, so it's not going to be major difference. The thing that's going to give us the biggest difference for this particular example is changing the sign that we're calling. So we're going to say from libc dot math import C import sign. Okay, so now we're pulling in the sign from the C layer now, and when we call sign inside of our function, it's no longer going to be any Python overhead. This is the Windows equivalent for that. Yeah. Yep. Math.h comes with it's really low level, so it's all ready to go. So let's give this a try now. And now we have, factor of 4-ish speed up. Okay, so that's at least on my system. Question? No, you don't. You see it off x inside of the function? Yeah, that shouldn't be the case because this is the double x here, the argument, that's declaring x as a C double, right? So what are you declaring as a inside of the function? You're saying if you did, it was a typo in the slides because you should only ever declare something as a C integer, C type once inside of Cython, okay, for a given function.
In fact, if you do a C def double x, you're going to get an error.
You get an error, yeah.
But that was for other.
For other variables, for different variables. That's right. So yeah, if you look here, let me show you. So for instance, here with distance, you're defining the arguments, but you're also defining local variables inside of the function body, but they're different variables. Yeah. Okay. So in this particular instance, most of the benefit comes from getting rid of the Python overhead when calling the sign function. Okay. So that's where the benefit comes from. In other instances, most of the benefit comes from just statically typing your arguments, and we'll see that in the capstone exercise here later on today. Okay, so I just want to emphasize to you that typing arguments and making sure you're calling functions at the C level are two of the most important ways of getting good performance out of Cython. Okay. Okay. So,
Changing the libc math, C import,
Oh, okay. There you go. Question? Yeah.
So if you do malloc and you don't free it, is it going to blow up
That will.
Python and Python, or does it kind of
That's a potential.
safely?
No, that's a potential memory leak. When you call malloc, you're responsible for calling free.
And so it'll screw up everything. It won't just, there's no
If you call free, it won't screw up everything, but
right.
but yeah, you're responsible for freeing that memory after you're done using it. Yeah, that's right. Question?
I wanted to point out that I know you kind of shared it for the NumPy data, and use Cython to speed up.
Certainly, yeah. There are definitely other ways to do this, and I'll talk about JIT compilers later on, that sort of thing. This is just baby steps for our larger example later on. So.
Using vectorization in your file to speed up that up.
So we are using NumPy's vectorization here along with Cython, but. Oh, I see what you mean. Yeah. Well, I guess, yeah, okay, I see. Do you have a version of it and it's faster than Cython? Oh, very interesting. I'd like to see that. Yeah, thanks for pointing that out. Yeah, this is not anything necessarily. There's even a sync function that comes with Python. So again, this is just for our first stops in typing our own functions and the concepts of what you use for speeding up code with Cython. Yeah.
Work with this. Would it be easy to tell that Cython's taking most of your time?
There are Cython profilers that kick in, and we'll see that here in just the next slides. So thank you. Nice lead in. Yeah.
So let's say I've written the whole code in the Cython way of it,
Mm-hmm.
and then if I selectively want to either do quickly Python and Cython, is that doable?
Yeah, you can. We'll see that as well later on, using a single source file that can be both Python and Cython at the same time. Okay, so there's this fantastic thing in Cython called Cython annotations. So if you want, you can tell Cython to generate a annotated HTML file that gives you feedback on which lines in your file are likely to take the most runtime. So here's our fib function from before. And let's see, what I'm going to do, go back into my demo and fib directory here. And here's fib.pyx. So again, here's our fib.pyx file. And I'm going to say now, I'm going to call Cython from the command line. And I'm going to give it the flag -a and give it the argument, the file fib.pyx. And when you call Cython from the command line with a pix file, it generates your C or C++ file for you. With -a, it also generates an HTML file, in this case called fib.html. Let's open that up. And we get this. Okay, again, for those of you following along, I'm inside of my demo fib directory, and I did Cython -a fib.pyx. That's all you have to do. Windows, Mac, Linux should be the same. That will spit out fib.c and fib.html. Okay? And now we just opened up fib.html in our browser. Okay? Open is a Mac command, so I don't know if it's available on, I don't know how you do this in Windows necessarily, but nor on Linux actually, sorry. Oh, okay, there you go, thanks. So Google Chrome on Linux would open it up in Chrome. Double click on Windows, thanks. I should have guessed. All right, so here we have this very nice annotated file now, and it's got this color coding going on. Actually, I kind of got ahead of myself. Let me do the same thing. Here's fib.orig, the original fib file, without any typing at all. Okay, so it's just pure Python code put into a PYX file. I'm going to do the same process on this file and compare. So Cython -a fib.orig.pix, And it spits out fiborig.html. All right, so this one now, we're going to compare the two of these. So here is the original without any typing information, and you notice there's a lot of yellow here. Some lines are deeper shade of yellow than others. And if you double click on one of these lines, it'll expand into the generated C code. Okay? And this is all the C code that Cython's spitting out for us. There's a lot here, right? If you look at it, it's got a lot of name mangling and stuff and that sort of thing. And most of this code is just dealing with reference counting, type checking, error checking, and error cases. That's most of what's going on here, but it's going on all over the place because we're dealing with Python objects, okay? And so there's a lot of overhead here, and you get a direct feel for that when you look at this code. All that has to go on at the Python level to run a simple for loop, for example. Now, this isn't the same thing that your Python interpreter is running. It's running bytecode and a virtual machine, that sort of thing. But it's still performing, underneath the covers, it's still performing essentially these same operations. Okay. So the color coding here is such that the shade of yellow corresponds to the number of lines of C code that are generated. And that actually turns out to be a fairly good heuristic for determining which lines are going to be the most, are going to hit you the most performance-wise. Okay. So if you click on this line here, we have, this is when we do our multiple assignment and our updates and that sort of thing. Whoops. And if you look here, it's calling pi number adds. This is a very general addition operation at the top here, but at least Cython's able to detect that A and B are numbers. So it's able to do a more specific addition rather than just the general Python addition where it looks up the add operator on two general Python objects, that sort of thing. So it's a little bit faster than if you were to run this just in pure Python. So anyway, that's our original function. Now let's go over here to our Cythonized version of the same, and you immediately notice that there's much less yellow here. And if you click on our for loop now, this is all C comment, so ignore that. This is our for loop now. Okay. Cython's able to generate a C for loop using C integers as the looping variable, and so forth. So even though we're writing in Python here, it's generating a C for loop for us here. So that's one big reason why the Fibonacci function, the Cythonized version of this, is much faster than the Python version of the same. Okay. If we click on the body of our for loop, you see it's just several assignments, but there's no Python in here at all. It's all just C assignments, C temporary variables, that sort of thing. So this gives you a very nice way of figuring out which lines of code are generating a lot of C code and more than likely leading to a slowdown in your Cython code. Okay.
If I have only the first and last line yellow, can I assume, or is it an assumption that that's the best?
Thank you for mentioning that. Yeah, that's very common in this sort of thing, and it's only because if you click on this, this is all the overhead. There's a lot of overhead here for just calling a Python function. So there's a lot of code that has to be done for doing that sort of thing. Correct. That's just you're stuck with that. That's right. Although it is generating a lot of code because it's trying to get around the slow parse tuple stuff that you would write manually if you were to do this by hand. But there still is there's just a lot of work to be done to take a general Python object and extract a C integer out of it and do it so that you do it without crashing your Python interpreter. Okay. And lastly, the return line here, there's just a lot of cleanup that's going on. And often, so the first line and the last line of a function are often yellow, and you can't do much about it. Okay, so that's our annotated source file. I didn't have time to go into it in the tutorial here, but there is a way to have Cython hook into the C profiling module inside of like Python C profiling module so that it can basically report on the runtime for specific C functions that you define using Cython. Okay, so I would encourage anyone who wants to talk about runtime performance of Cython code and profiling that to look into the Cython documentation online. Okay, so that brings us to our sync exercise, which you already did. But we can at least take a quick peek at the difference in the annotated sync file. So let me just do that really quickly, just to give you another peek at that. And then we'll have our break. So I'm going to say Cython-a sync kernel. Oops. Let me just do the Python file. So Cython can use .py files as source. They don't have to be just pyx files, and it'll just treat it like it were a pyx file. Okay. Since Cython is more general, it's a superset of Python. The Python language, you can just give it a python.py file, and it'll work just fine. Okay. So let's take a look at that. Sync Python HTML. So here's our Python version of sync kernel. You see there's a lot of yellow here. This line in particular, there's a lot going on. And down here, calling sine of x over x. Let's see if we can find the sine call in here. Interesting. So there's a pix get name, which is doing a general Python lookup of the name sine. So if it doesn't find it locally, it's going to look in the module scope, and it's going to find it there. If it wasn't there, look in the built-in scope to find it there. So it's doing a general name lookup every single time. It's creating a new argument tuple. It's sticking our argument inside of that tuple, that sort of thing. So it's doing all very general Python level stuff to make this work. So let's see the Cython version of the same. So we're going to say Cython-a sync Cython. Oops, sorry. Sync kernel.pyx, that's what I want. Gives us an HTML file, and you see it's not quite as much. This line is now white rather than yellow, so it's much better code generation there. This line here, let's see if we can find the call to sign in here. Sorry, does anyone see it? That's the return stuff. Oh, here it is. So here, it's just calling sign as you would call it in C, okay? So it is generating the equivalent C code that you would write yourself. And it doesn't have to do a general get name to find the sign object and then call it using an argument tuple, that kind of stuff. So very different code that's generated here since we're importing sign from the C library now, okay? All right. So that's our sync exercise. That's a great spot to stop for our break. So we'll break for half an hour, is that right? Okay. We'll say 3:20. Let's come back and start ramping up again, okay? So about half an hour.